Thank you. Okay, so if the last one was the boring talk, this is the exciting talk. This is the engine that we build on top of the brakes that I spoke about before. And we don't do this by throwing more hardware at the problem. We're going to actually change how execution and time interact with each other. And it's about finding the limits of what the blockchain can actually do without overstepping them. So there's two things that a blockchain does. There's consensus, which is how the nodes agree on things, and there's execution, which is how they decide what to agree upon. And they're very tightly coupled at the moment, and not in a good way. They should collaborate, but really what they do is they take turns getting in each other's way. So here we have consensus and execution, and they don't play nicely together. This is the current state. Red is time spent on execution, gray is time spent on consensus, and time is moving left to right. Most blockchains, and the C chain as well, at the moment, they execute and then they agree. There's a little bit of time during agreement where the other nodes also run the execution. And what you can see is you have this A, context switching, and B, this waste of time as a result. And so they bounce between the two, but they're never doing both of them at once. And you get this really awkward symmetrical bottleneck. Each job is always waiting for the other one. So when you're executing, you can't be agreeing on it because you need that, and vice versa. And this is the current state that we've got at the moment. It is possible to make this asynchronous. It's a good start. You decouple the two. And what you do is you do that by having a fixed block delay. So you come to an agreement on the transactions that you will include in the block. That's happening there on the far left, and their order. Because everything from that point onwards is deterministic, it's okay. You don't have to execute them straight away. You can say, we are going to get back to getting those results, and then move on. So you pass it down to the execution queue. You say, okay, you execute that, you get back to me, in this case, in 2 blocks' time. The results from this execution come up to this agreement, and they come back and forth like that. You have to do that safely, though. You can't just put an arbitrary amount of execution onto the executor stream and just say, get back to me by the next block, because if you've put too much on, it's going to take too long, and you'll slow the chain down. The only way you can actually know how much to put into the executor is by looking at the gas limits. So every transaction specifies a gas limit of the most amount of compute and resources that it will consume. And that is until you actually run the transaction, you can't know if it's going to use that or not. So that's what I've demonstrated here in this dead space. That is the gap between the user-specified limit of what they are prepared to pay for and then what it actually uses. So yes, you've bought yourself some breathing room, saying, okay, we'll execute a little bit later, but you're also then leaving your CPU idle because you've allotted and overestimated how much time to spend on execution. So that's an improvement over the synchronous case that we have here, but we still have that dead space. So we had before consensus and execution, now we have a cool cat, not an annoying one who gets in the other's way. How can we completely decouple them? What if execution didn't have that deadline that said you have to get back to me by this time? And if you don't have a deadline, you don't have to estimate the deadline. So that was the question we asked ourselves. How can we achieve that? So what we do is we maintain a queue of blocks that will get executed. We know from before that execution is deterministic. If we know the transactions in their order, we know what will come out of it. But if we know that, it's also deterministic how long it takes, as measured in cycles. So you can think of gas as like a CPU cycle. And if we measure it like that, then we know how long it's going to take. And so the core leap that we get from this setup is execution doesn't work to a deadline. It defines the deadlines, and then it reports back later. So I'll give it a worked example here. At first, we agree on a block, and we push it to the executor queue. It just so happens that it finishes in time, that it gets reported 2 blocks later. Consensus moves along, it pushes a block to the queue to get executed, and it starts executing. By the time consensus moves along, it hasn't actually finished. The next block pushes later on in the queue, and so on and so forth. And we'll see that as soon as a block is finished in time, it will get reported. These 2 blocks get reported later, and that's all because we have a deterministic measure of both results and of execution time. The process ends up starting again because the queue has stopped. The queue was cleared because consensus happened to push not enough. There wasn't enough demand at that time to saturate the execution queue, but it continues. And then it just so happens to start again. You'll see that the blocks end up getting smaller. That's because the gas price goes up. The consensus queue still has an idea of what gas is going to be and will only push transactions and blocks if people are willing to pay that gas. So as the queue gets longer, the gas price also goes up, and that naturally gives you a feedback mechanism to rein things in the same way that gas works now anyway. The queue also has a maximum size, which acts as a back pressure window, just like back pressure in TCP. So we've thrown out this deadline. How do we actually have a way to have a clock? We don't have a clock anymore, so we need to use our own. So ACP-196, the ACP that introduced current gas pricing, has this variable called R. It's generalizable enough that it can apply to any blockchain, and it just says, what is the execution throughput that we can sustain? For every second, how much gas can we use? And that's a concept that's not new. What happens if we turn this on its head? We can say, if we consumed a certain amount of gas, and we know the amount that we're prepared to consume per second, or able to consume per second, we suddenly have a measure of time. So if you burn gas, you burn time. And that gives you a way to deterministically compute the execution timestamp of the end of a block, so you know when to feed it back into consensus. You can't just throw things onto a queue and hope for the best and go, oh, let's check our watches, see when it's done, and then we'll all report back. Clocks differ, computers differ in their speed. You have to have a way that everybody can agree on this timestamp. So in streaming asynchronous execution, sorry, I always call it SAE because it's a tongue twister. So in SAE, anytime that we talk about time, we're actually referring to gas time, not wall time. So what happens, as I mentioned before, is that execution just goes along, just churns through the transactions that it gets given, while the consensus locks in the results a bit later. We don't do this straight away. We delay by a few seconds as a way of smoothing over any arbitrary latency that we incur. So if the database needs to compact at that point in time, we don't want that to affect just that block. By spreading out the settlement time, that gets averaged out, and it only affects the window instead of the single block. And what that does is it means that we can tune the chain to work for average time, not worst case scenario, which is a great improvement. You haven't changed any of your hardware, you haven't changed any of your implementation. All you've done is said, we are now capable of handling the spread out latency, which means you can dial things up a little bit. And what does it record? So it's the state root, which is the Merkle tree root of the state at the end of all of the execution, and all of the receipts since the last settlement. So what you're used to at the moment is that every block has all of the transaction receipts in a Merkle Patricia tree. This is just all of the previous blocks. However, the API won't change. If you make an API call and you ask for a particular block, or you ask for the receipts from a particular block, you'll still get the old things. From the outside, it looks the same, but on the inside, it's got this change. Despite this, the delayed settlement is only for the chain. It's only so state sync can work, and so that machines can check that they haven't diverged through an extremely rare chance of like a hard drive malfunction or something like that. From the user perspective, once your transaction has actually been executed, you can receive a receipt immediately. What that means is if your transaction happens to be at the beginning of the block, you'll get your receipts before the transaction that happens to be at the end of the block. So this delayed settlement is not actually slowing you down. It's a small speed up by being at the beginning versus the end, but it's not a slowdown, which is the important part. What's the effect of this? So it's actually a little known fact that when Henry Ford invented assembly lines, it was for blockchains, not for cars. It's actually useful to think of the execution stream now as an assembly line. It sits there and it just waits for blocks to be handed to it. Consensus comes along, agrees on a block, puts it on the conveyor belt, and the execution stream will then execute it when it gets to it. So we get faster block acceptance because we are not having to do the execution before doing it. We're dedicating all of the time to acceptance and consensus. Combining that with, once it's actually accepted, the execution stream is running, it's saturated all of the time. Without this, it's like having an engine where you, 80% of the time you're allowed to put your foot on the accelerator. Then they say, sorry, you can't run it all of the time. In this case, we can run the engine 100% of the time when there is demand that requires it, and people who are willing to pay a high enough gas price. Plus, you get your receipts immediately, as soon as it's executed. Put that all together, and from a user's perspective, this becomes extremely snappy, very fast. This is the thing I'm actually most excited about. I was describing the case where you have a Merkle tree. Not everybody actually is taking part in consensus. If you're not a validator, you don't need necessarily, if you don't want to, you don't have to have the Merkle trees. You can leave them behind. They're good for state sync, they're good for comparisons, but they add a lot of unnecessary overhead. They slow things down. As you build up that tree, you perform all of the hashing that goes up, it wastes your time. So if you trust the node that is performing the execution, and it's up to you, you can choose to not actually Merkleize your tree. And that means that when you move through that execution stream, you can go much faster. In a permissioned chain, where the queue is allowed to grow even longer, you can see the future. The validators are chugging along. If you're running a lean execution client, you're already at the end of the queue. So a block explorer can give receipts immediately and faster. This is a cool thing. If you are a custodian and you know which addresses are EOAs, so you know that they're not necessarily, you know it's not going to run code, you can actually filter the queue. You just look through and you say, only pull out the addresses that are EOAs that I own, and I know that they are actually going to succeed. As soon as you put a transaction in the queue, it is deterministic. You know that it's going to run, and you know how it's going to run. If you are the owner of the recipient address and you know that it's an EOA, you know that those funds are going to come in. So if I'm a custodian and I want to credit people's balances for whatever reason I want to go faster, you can just do that immediately. You don't actually have to look at the queue. You don't have to execute anything that comes before it. I don't come from the world of high-frequency trading, but my understanding is they want all of the information that they could get, and they want it yesterday. So they can use this too. Suddenly they're working at the tip. They know where things are at the end of this execution, and they know the state there. How do we do this safely, though? So anyone who's ever read about cryptography, they know about Alice and Bob. Not everybody knows about Mallory, their malicious counterpart, and we want to price her out so she can't attack the chain. We need to make sure that she can afford to actually pay for transactions. It's important to note, consensus just cares that Mallory can pay. Whatever happens afterwards doesn't matter. So transactions can still revert. Just because they're on the queue doesn't mean they can't revert. That is a normal thing. For example, if you specify a slippage limit and it goes beyond that, you want it to revert. But what we're interested in here is how do we know that anyone pushing something to the queue is actually going to be able to pay for it? So our gas price is an exponential curve that runs like this, and that's something called monotonic. If you increase the input, you're going to increase the output. What we do is we assume that every single transaction that's going into the queue is going to use its limit. It's going to use the maximum amount of gas possible. And what that does is it means for every block that we reach in the execution stream, it's going to have the highest gas price, if that were to be the case. So if we assume that every block is going to move as far to the right as possible, the price that that block will face will be as high as possible. It'll be these dotted lines. When you actually execute and you find that you've used less gas, you end up with a far lower price. And so we're guaranteed that people can pay. So building something like this is why I gave my talk earlier. It's why we spent all of that time building breaks, building something boring by design, so that we can then go and do something like this. It's the groundwork that we build up on top of. So together what we're doing here is we're building these fast systems in a way that remains, from an engineering perspective, safe to do. You've seen the engine and you've seen the brakes, and thank you. You got any questions?
Do we have any questions for Arran? Over here.
We were given a slide template, and I just had to figure out where to put this.
You touched upon it already in the talk, but I didn't fully grasp it. So if you have this asynchronous execution, and from the user side, so you submit the transaction, in which block does the transaction actually end up?
We'll get there. Yeah, okay. From a user's perspective, which block you end up in is the same as before. So this top level is the same as there is a block builder or proposer pulling transactions from the mempool and placing them into a block. So you can imagine there's a mempool on top, and whatever priority mechanism the builder is using at that time, they will propose it here. Consensus will agree upon it in the same way as before, and then it's the bottom, the separation from top to bottom is just when it gets run. It's nothing to do with which one you get placed in to be executed. The block that you get placed in decides your priority and when you will get executed relative to other transactions. Yes. Okay, so you don't know the result yet. You will know the result when this stream here, these timelines aren't necessarily the same. If you look in gas time like we described it, then it's the same. But really the wall time of the CPU will move much faster than this, and you'll get your result immediately. You'll get your result far sooner than you would have before.
Okay, but I still don't know how it turns out, right? Before the execution is done.
Yes, but it is determined. Yes, exactly. So you don't know how it's turned out before execution is done, which is the same in the synchronous case. You don't know what's going to happen, but it's deterministic. You will find out your result if you look at your watch time much faster.
Okay.
And I can explain after if you
sure.
got more questions. I think we had one more.
Thank you. Very interesting. I'm wondering how's the process for doing the research and development? Does it involve universities? It seems like it's very research intensive. So how is that process evolved? And how you decide upon one research line to develop? Then I want to know how more efficient is this process compared to the, like, how is it now? And then lastly, I'm a little bit confused. I always thought of like a blockchain like as a transaction function. So you have state, then you would apply the transactions, and then you would have an output which would be the new state, and that would be the input for the next block. So here, for what I understand, you are building a block, you're executing, but then the new block, as in you got the first block, it's being executed, and it's built up. Then how are you able to execute the logic if you don't have the state? I'm not sure if...
Yeah, I'll answer your questions in reverse order. So the state that you're building on is actually maintained by the bottom, the execution stream at the bottom. It is what captures the state and keeps the state. And all it does is it feeds a checkpoint back into Consensus to record it. So you are still building state on the last state. It's just a state machine like before. Nothing changes in that respect. What changes is when your block headers record it and what they record. But it's still state built upon state with transitions in between. As far as how we decide on what to work on, has anyone seen the XKCD nerd sniping comic? Yeah, anyone who's familiar with that? Basically, Steven said something one day, and I said, ooh, that seems interesting. And then I disappeared for a month, and that's how this kind of happened. The way that we decide on what things to work on over others is a little bit of gut feel of what we think will speed things up, but also quite objective. Like I show you the evolution of synchronous, asynchronous, streaming asynchronous. You can see if you're leaving dead space, that's a problem. So our experience shows us these are things that we need to tackle. Actual benchmarks are still pending. I would give you a fake benchmark that just runs on my laptop, but that would not be reflective of reality right now. What I can say is that it does actually run the execution stream 100% of the time, as far as like with the in-between transaction stuff as well. Whereas on the C chain at the moment, it looks like we're doing 10 to 15% of the time.
Awesome. Any more questions? You have a question over here? Or are you good now? Over here?
Does this change the block gas limit, or is there no limit at all because you're just paying for time now?
So time is gas. The window that is allowed, so if you stop thinking in terms of a block gas limit and you think of a time gas limit, that won't change. The amount that can get pushed at any single time does go up and is allowed to go a little bit larger than that, as long as it's small enough that Consensus can still use the gossip and all protocols to actually communicate this block. But for example, this block is a little bit bigger. So yes, it goes into it. It does increase the limit, but at the expense of what comes next a little bit. So what it does is it gives you bursty throughput. We already have bursty throughput, but this is an easier to understand and to rationalize throughput increase here.
Any other questions? Anyone? Is that a yawn or a hand raise? I saw that. Awesome. Round of applause for Arran, please. For Arran.